Okay, so this is going to be quite a heavy one. It's the Falconer's threshold model, but just stick with me here. I'll try my best to explain it. Essentially, you're going to have a population curve, right? And let's start off with standard deviation. Standard deviation is just essentially how far away you are from the mean. We usually have 3 standard deviations. They each include different amounts. I think one standard deviation includes like 66% of the population, then it goes up to like 95, 99, whatever it may be. The point I'm trying to make though is that we have a scale of standard deviations on the bottom, and let's call this scale the scale of liability, right? Now, let's look at a disease. Let's look at schizophrenia, for example. We can figure out through analyses and data collection that the average percent of people who, let's say, have schizophrenia is here, okay? This is our mean. This is our standardized bell curve. This is the people who have it, who have schizophrenia, random, at a population. That's the chance of you getting it. The reason why there's a bell curve is because certain people are going to be more likely or less likely to have it based on factors such as environmental factors, whatever they may be for schizophrenia. But the average is still here. Now, let's say you're an affected individual whose sibling also has schizophrenia, or who someone's uncle has schizophrenia. I mean, like your uncle has schizophrenia, or your parents, or something along that line. Well, we know that to some extent, schizophrenia is a genetically transferable disease. And as such, your chance gets pushed to the right because you end up having a positive scale of liability. Your chance of having schizophrenia, or your incidence, ends up being higher than the average. So your average or your chance is here. Now the problem becomes that certain diseases like schizophrenia are not entirely genetic. They're also based on environmental factors. And as such, we end up getting this difference here, but we can't really quantify it. So what we do is we get monozygotic twins. And the reason for this is because most of the time they share 100% environment, 100% genetic factors. And as such, they serve as a certain baseline as to who we can compare against to figure out, well, your uncle has schizophrenia, but we want to figure out your chance, but we also want to account for a heritability, which is how much of this trait was actually due to genetic factors and not just the environment being the environment, right? Because when we collect data from all these different individuals, this is kind of like a researchy thing, but I'm just trying to explain why we kind of have to do this. It's that every different individual has different environmental factors, different upbringings, different food, different nutrition, clothing, whatever it might be, that could somehow contribute to this disease. And let's say a certain group of individuals live in a certain area that we have surveyed, all have the same nutrition or something. That may be contributing to their chance of having schizophrenia. So by using monozygotic twins, we're equating the environments, we're equating the genetic factors, and we're essentially comparing the concordance in monozygotic twins relative to the curve for, let's say, relatives or identical twins, or really just the average general population, right? Now, there's also this thing called threshold, which is when you hit a certain liability or risk, you end up having the disease. So after a certain level of your cousins and certain genetic things, you end up, let's say, having the disease, which could be here. But your chance of being an affected individual could be there. Anyway, before this gets too complicated, the point is that there's this really nice equation that we can use. It's really not that bad. Essentially, you have heritability equals B divided by R equals XG minus XR, A times R. And here's a step-by-step of solving this problem. First, locate the incidence of in the population of monozygotic twins. So usually be provided for you. Then you can find XG and XR from the Falconer's tables. You can calculate their difference. Why are we calculating the difference? I don't really know. I think good thing I actually do know why we're doing certain things. I found the lecture slide. So essentially, our threshold, right? The threshold is where is the degree of liability, or to what standard deviation we're going to get the disease. Now, please notice that for the general population, you have a very high threshold, which basically means in the general population, the disease, at least the disease described here, is very rare. And that's our XG, our X general. So that's how far are we on a scale, because remember, we need to quantify things, from getting the disease. So very far away. Versus if you have relatives who have the disease, kind of similar to how I was saying it before, here is your XR, so your X relatives, right? And obviously, if your relatives have a disease, there's a very high chance that there is genetic lineage, if you will, in your family, and as such, you are more likely to have the disease. And so the threshold is way closer to the mean of average people. Hence, it is more likely that you're going to have the disease. Now, in terms of equilibrating them and finding out their difference, that's why we're doing XG minus XR. That's giving us the difference between the two thresholds. How likely are you to have it in a general population? How likely are you to have it for relatives? Now, notice that which type of relatives was not defined. That's why we're dividing it by our A and R, because that's kind of what's differentiating between the twins, uncles, and so forth. That's what the R is doing. And the A is just the mean standard deviation of affected individuals in general. So essentially, it's going to allow us to figure out how much of our genetic factors are contributing to our disease, while using the standardized way of using monozygotic twins, figuring out a difference between the general population threshold versus our relatives threshold, and then equilibrating it to the type of relatives that we're having, so using our R, all divided by our mean standard deviation of affected individuals. So how much difference did we get from the mean difference? And let's multiply by R at the bottom just to quantify where those relatives are siblings or uncles, grandparents, whatever they may be. To me, I'm just looking at it as a formula and how to plug in the numbers, but please do try to figure out why we're doing certain things that may help the formula stick better as per your learning styles. And then we're going to have A, which is from our Falconer's tables, and R. R is just like a coefficient. There's a couple that you have to remember. I think it's like 1, 0.5, 0.7. It'll be covered in lecture, whatever it is. But essentially, it just allows you to differentiate between twins, uncles, and their relative relatedness. So you're going to have a different correlation factor if someone's your sibling versus your uncle. Like your sibling's going to have more genetic closeness with you. So that's kind of the best way I can explain that. In terms of A, this is your mean standard deviation of your affected individuals, or really your mean liability of affected individuals in general population. Why are we calculating this difference? Essentially, we're just trying to figure out how far has this curve moved against the other one. How far has the relatives curve been pushed to the right? Essentially, there's this question, which is that fraternal twins, their chance was 17%. Their regular incidence is 1%, or R is 0.5 because they're going to be twins. Calculate heritability using Falconer's tables. So what we do is we get our XG from our Falconer's table. This is by using our percentages. We minus our XR, and then we just divide it by our A, which is from our Falconer's table as well, and our 0.5, we get 1.03. Yes, you will be provided a Falconer's table in the exam. You do not have to memorize it. I'm going to try to pull up an example just so I can show it. So essentially, you're going to go to your Falconer's table. Remember, the fraternal twin chance was 17%. So we go to 17, and we find our X right here. This is our XR, okay? And so 0.954, and our A is not 1.48, it's actually 2.665. So that's going to be our XR because that's off to 17%, so that's 0.94. Now though, we have to look at our A's, and so we're going to want to scroll all the way up to 1%. So remember, the regular incidence of having these twins was 1%, right? Versus the fraternal twin rate was 17%. So now we're essentially comparing how much have we moved to the right on the top divided by our regular incidence multiplied by our I guess twins rate. So essentially that's where we're getting our 1% from. That's going to be our A, right? Because what our A is essentially the mean standard deviation of our affected individuals. Therefore, that's where the 1% is coming from, and we're using 2.326. So that's where we're getting our 2.326 minus 0.954 divided by 2.665 times 0.5. I feel like I haven't done a good job explaining it, but I've honestly tried my best. Just go over a couple practice questions. I think that'll help solidify a method for you